Hey everyone, and welcome. Today we're jumping into something absolutely critical for anyone who works with data. We're going to talk about how to take a conceptual model, the architect's grand blueprint, and actually forge it into a real, working relational database. Let's dive right in.
So, here's our game plan. We're going to tackle this in 4 key steps. First, we'll cover that foundational translation, turning ideas into actual structures. Then we'll get into the challenge of making sure every single piece of data is unique. After that, we'll see how to build bridges to connect all our data tables. And finally, we'll look at creating simple, custom lenses so people can see the data they need without all the complexity.
All right, let's kick things off with part 1, the foundational translation. This is really the most fundamental step. It's where we bridge that huge gap between a business idea and the actual database technology.
Okay, so imagine you're the architect. You've done the hard work, your model is perfect, it defines all the key business concepts like customers and products as entity classes and their details as attributes. But here's the million-dollar question. How do we get a database which just thinks in tables and rows to understand what a customer even is? Well, the designer's answer here is actually pretty elegant and surprisingly straightforward. Every single entity class from that conceptual model directly becomes a table in the database. And every attribute you defined, that becomes a column inside that table. It's a clean, direct, one-to-one mapping. Simple as that.
Now, a table is really the heart of a relational database. The best way to think of it is like a spreadsheet that's hyper-focused on just one single subject. So each row you add is one specific instance, one customer, one order, and each column is designed to hold one specific piece of information about it.
Okay, so we've got our tables. But that immediately brings up the next big hurdle. In a database, there's zero room for ambiguity. We absolutely need a guaranteed way to find any single piece of information we're looking for.
From an architect's perspective, this is a huge deal. I mean, think about it. If your customer table has thousands of people, and 2 of them are named John Smith, how on earth does the system tell them apart? We need a completely foolproof method to make every single row totally distinct.
And this is where the designer steps in with a crucial concept, the unique key. And this isn't just a friendly suggestion, it's a hard and fast rule. We pick 1 or more columns that, when you put them together, create a value that can never, ever be repeated in that table. This key becomes the official unique ID for every single row.
Now, these unique keys come in a couple of flavors. Every table must have one and only one primary key. This is the big one, the main identifier for a row, and it can never be empty or null. But you can also have alternative keys. Think of things like a unique email address or user ID. They're secondary ways to pinpoint a specific row.
So our data is now sitting in these nice, separate, well-identified tables. But the real power, the magic, is unlocked when we connect them. This is what puts the relation in a relational database.
Right, so here's the next problem from the architect's corner. My conceptual model clearly shows that a customer places an order. That's the relationship. But in our design, customer lives in one table and order lives in a completely different one. How do we build a reliable bridge between a specific order and the exact customer who placed it?
The designer's solution here is a real cornerstone of database design, the foreign key. It's a simple idea, but it's incredibly powerful. You basically take a copy of the parent table's primary key, like a customer ID, and you place it in the child table, like the orders table. This creates this unbreakable logical link that guarantees an order always points back to a real, valid customer.
And setting this up is a really clear 4-step process. First, you identify your parent table, say customer, and its primary key. Then you identify your child table, like orders. Step 3, you add a new column to that child table to hold the parent's key. And finally, you officially define that new column as a foreign key, which tells the database to enforce that crucial link.
Okay, our database structure is really taking shape. We've got tables, we've got unique keys and foreign keys connecting everything. But for the person actually using this data, this can start to look really, really complex. So let's talk about making things simpler.
And that's exactly what the architect is worried about. We have to think about the end users, right? They shouldn't have to navigate a dozen different tables and understand all these keys just to see a customer's recent orders. So the question is, how do we shield them from all that complexity and just give them a clean, simple window into the data?
Because if we don't solve this, here's the nightmare scenario. Every single time someone needs that complete picture, they have to write this complicated query, manually joining the customer table to the orders table, then maybe the order_items table to the products table. It's repetitive, it's easy to mess up, and it's super inefficient.
But of course, there's a much smarter way. The designer solution here is just beautiful. It's called a view. A view is almost like magic. It looks and acts exactly like a regular table, but it's not actually storing any data. It's really just our complex join query saved with a simple name. All that heavy lifting happens behind the scenes.
And look at the difference this makes. All that mind-bending complexity is now hidden away. Instead of writing that massive query, a user can just ask for everything from the customer orders view. It's way simpler, it's more secure since you can control access, and to make sure everyone is looking at the data in the exact same consistent way.
So let's just quickly recap the 4 absolute cornerstones of this whole process. We turn our abstract concepts into concrete tables and columns. We enforce uniqueness with primary keys. We build those crucial relationships with foreign keys. And finally, we simplify access and add security using views. Nailing these steps is the key to any great relational design.
All right, I want to leave you with a question to chew on. We've just walked through how to translate a model into the very structured relational world. But how do these fundamental ideas, identification, relationships, and simplification, how do they change or maybe even hold up when you're designing for the super flexible, non-relational world of NoSQL? Definitely something to think about.
Hey, if this helped you connect the dots, we'd love it if you'd hit that like button, share it with a friend, and subscribe for more explainers that bring theory into practice. Thanks for watching.